Good morning, good afternoon, good evening, class. This is Mr. Arosena, and today we're going to continue our study of functional operations by studying how to take the product and quotient of functions. So, as a quick reminder, last time we talked about addition of functions, and it basically was take f of x and we just add it to g of x. There we go, that's how we add functions. And then we expanded that into subtraction of functions, which is basically f of x minus g of x. Okay, so that's what we did last time. Okay, so function addition, function subtraction. Today we're going to talk about how to take the product and quotient of functions, which is unsurprisingly very, very similar to how we add and subtract functions. Let's get right to it. So, first, a product of functions is just like a product of numbers. All we really do is we take f of x and we multiply it by g of x. So, symbolically, this would look like this. My new function, which we'll call h of x, and we just multiply the two functions together, so it's basically f of x times g of x. There you go. That's how we multiply. Now sometimes it can be written like this, f dot g, not to be confused with open dot, which we'll talk about another day. Okay, there we go. So this is a product of functions, f dot g, or f of x times g of x, or sometimes it'll be f times g of x. Okay, and that's how you take the product of a function. Okay. Right, nothing really else more to it than that, and we'll get to some examples shortly. Okay, so after taking products of functions, we can do the exact same thing with quotients of functions, and that's basically just one function divided by another function. So if I have my combined function h of x, the quotient of functions is basically just going to be one function divided by another function. And this is incredibly similar, or you treat this incredibly similar to how we dealt with rational functions. Because if you recall, a rational function, I'll write it up here, rational function, or definition of a rational function was, actually now when I think about it, exactly the same. F of x divided by g of x. So a quotient of functions is really just a rational function in disguise. Sometimes you can write a quotient of functions as follows: f divided by g of x, like that. Okay. So these two are equivalent. If you see this, it really means this, and then vice versa is true. Okay. Yeah, so that's how we can deal with quotients and products of functions. So reminder, a product of functions is just two functions multiplied together, and this is how they look like. They either look like f of x times g of x or f times g of x. And then a quotient of functions looks like this, which is just f of x divided by g of x or f divided by g of x. Okay. And when you look at it, a quotient of functions is really just another name for a rational function. Okay. Right. Now, one thing I did not talk about last lesson was domains of combined functions. Okay. And we'll talk about that now. Now we know that we can create functions by adding, subtracting, multiplying, and dividing. Now, what's common between all of these is that to find the domain of the combined function, all you really need to do is find what domain. So I'll highlight here, what domain is common. So this means that both f of x and g of x exist in that region. Okay, and we'll go through some examples of this, or we'll explore this concept a little bit more. Some of the examples we'll go through today. Okay, we just got to remember that if you have a combined function, the domain of the combined function has to be both common to f of x and g of x. If f of x doesn't exist in some part, then the combined function obviously shouldn't exist in that part either. Similarly, if g of x stops existing at one part, then the combined function won't exist in the part that g of x doesn't exist in. Okay. Alright. So that's how you find the domain. Range is actually quite a little bit more difficult, and to find the range, so range, your textbook puts it simply just use the graph. Use the graph. Use the graph of combined function. Okay, that's really the easiest way to find the range. Okay, at this point, there's no real, algebraic solution. At least your textbook doesn't describe it. Okay, there is a way to determine algebraically, but I'm not going to go through it. All right. Okay, so let's go to the first example. Example 1. Here we go. So we have two functions, f of x and g of x. F of x is 2x plus 3. G of x is x minus 2 all squared. Determine the combined function f of x times g of x, and then determine its domain. Alright, so h of x we know is just f of x times g of x, so I can write it down as follows. 2x, let's not do that. 2x plus 3 times x minus 2 all squared. And let's expand this. Well, you probably don't really need to expand it, but we'll expand it anyways, because it's fun. So, this will be 2x plus 3, x minus 2 squared. If I use my square double square technique for squaring a binomial, this will be x squared minus 4x plus 4. Okay, I can continue expanding this to give me the following. This will be 2x cubed minus 8x squared plus 8x plus 3x squared minus 12x plus 12. Now you can clean up some of the like terms. So 2x cubed. We have a minus 8x squared and a plus 3x squared for a combined minus 5x squared. We have a plus 8x and a minus 12x to give us a combined minus 4x and then a plus 12. Right, and here's my final complete function after I multiply f of x and g of x. Now, time to determine what is its domain. Well, looking at this, this is just a polynomial function. So this is a polynomial function. Polynomial function. And from earlier, when dealing with polynomial functions, we know that the domain of any polynomial function, okay, meaning it's just a series of terms, x can be found in all real numbers. And that's true for all polynomial functions. No, it's not a rational function, because if it was a rational function, there might be restrictions based on what the denominator of the function is. Similarly, there's no radicals, so we don't have to worry about that, because again, some radicals don't have, some radicals do have restrictions. Okay, but for a polynomial function where there's nothing else happening, just a bunch of powers of x, domain is all real numbers. Okay. Finding the range is a little trickier because algebraically it's a little more difficult to tell, but we do know that this is an odd polynomial function because of the highest power is a 3. So highest power is a 3, so it's an odd polynomial function. So we'll say odd polynomial. And one neat property about odd polynomials is that its range will be all real numbers. Okay, because it goes down to negative infinity all the way up to positive infinity. Now, if you want to check, we can always graph it. So let's graph it. So it is 2x cubed minus 5x squared minus 4x plus 12. Let's throw down the projector mode. As expected, the range of the function is all real numbers because it's going down to negative infinity and then going up to positive infinity. And like all their polynomials, it will exist for all values of x. Okay. There you go. That's how we That's how we multiply two functions together, and we can use that to help us determine what the domain is. Okay, right. Let's go to the next example. Example 2. So here's a slightly different problem. We have two functions, f of x and g of x. One is, or f of x is x plus 3, g of x is square root of x plus 2, and we want to determine what is h of x, which is g of x divided by f of x, and what is its domain. Right, let's get started. Let's switch to a different color. Alright, so g of x is square root of x plus 2. F of x is x plus 3. We can't really simplify it any further, so we just leave it as it is. There's my h of x. Now domain. So the domain has to be in a spot where both f of x and g of x exists. So let's take a look at g of x first. Well, maybe not g of x. Let's go f of x first. F of x is first. So in f of x, since it's just x plus 3, this is a linear function. So the domain for f of x is going to be, x will be all real numbers. That's easy enough. Okay, so x has like no restrictions. Again, because it's a linear function, there's no restrictions. Now g of x, however, does have a restriction. Because if you look at g of x is a radical. And radicals generally have restrictions unless they're odd radicals. But this is an even radical. And just as a reminder, if we don't have a number there, we consider it to be a square root. So radical with, I guess, 2. So in this case, we know that x has to be greater than or equal to some number. That number is basically what this number here cannot be 0. So x plus 2, sorry, it has to be greater than 0, greater than or equal to 0. So when we solve that, we get the following. X has to be greater than or equal to negative 2. Okay, so here are the domains for f of x and g of x. Now the domain for h of x has to satisfy both. Okay. The domain of h of x can't be all real numbers, because if it is, then it kind of invalidates g of x. So g of x has a restriction of it has to be greater than or equal to negative 2. So our domain for h of x will end up being the domain of g of x, because if x is less than negative 2, then it stops existing, simply because g of x stops existing. So the domain of the combined function ends up being this. Okay, there we go. Now the range, trying to figure out the range, no real easy algebraic way to do this, so we'll just graph it. Alright, so let's graph it. Square root of x plus 2 divided by x plus 3. Alright, this is a little tricky. Alright, so as you can see, the range looks like it is greater than 0 on this part. Looks like it doesn't get higher than 0.5. So it looks like the highest possible number is 0.5. I'm going to zoom out. And it looks like that's about it. So the range appears to be, based on the graph, this is the highest point, because everything else is lower than it. Yeah, everything else is lower. So it appears then that the range is going to be y is greater than or equal to 0, but it is also less than or equal to 0.5. Yeah, so that's my range, based on graph. Based on graph. Based on the graph. Okay. Now part of this kind of makes sense, because if you think about it, the y greater than or equal to 0 arises from simply because the numerator, smallest value the numerator can have, is going to be 0. It can't be negative because the square root, by convention, we take the square root to always be positive. So the smallest number that it can be is going to be 0. Okay, so that's where this part of the domain comes in. The rest of it, this part, you can trial and error, I suppose, to figure out what the highest point is of that, but at this point, we can just use a graph. Using a graph is probably the easiest, at least for determining range. Determining domain is fairly easy because you just have to use a different color. For determining range, again, you just have to look at the, or domain, sorry, determining the domain, you just have to look at the domain of your combined functions and decide what conditions will satisfy all of those domains. Alright, one more example. Example 3. Alright, so here, given f of x, we have two functions. Determine what the combined function is and determine its domain. Alright, so let us check this out. So f of x is going to be x squared minus 5x plus 6, and we're going to be dividing this by g of x, which is x minus 2 all squared. Alright, now in example 1, there was nothing we could do to simplify that particular example. Same thing with example. No, sorry, not example 1. Example 2, we couldn't simplify. This example we can, though. Okay, because we have a quadratic in the numerator. And what can we do with quadratics? If you remember, well, hopefully everyone remembers this, you can always factor, or you can try to factor quadratics. You can't always factor a quadratic, but you can try. This particular quadratic should be able to factor to x minus 2 and x minus 3, if I'm not mistaken. Okay. And I'm going to write the x minus 2 squared as x minus 2 times x minus 2. Now, the reason I wrote that, or expanded the x minus 2 squared, is because in this form, it's fairly easy to see what we can do next. The x minus 2 in the numerator can cancel one of the x minus 2's in the denominator, so we now get the following. X minus 3 over x minus 2. So the combined function of f of x divided by g of x gives us a fairly simple function, x minus 3 and x minus 2. Or x minus 3 divided by x minus 2. Now, let's determine the domain. So again, we'll look at the domains of f of x, and we'll look at the domain of g of x. So f of x has the following. It's just a quadratic. All quadratics have domains of all real numbers. Okay. G of x is also a quadratic, albeit in a slightly different form. So g of x will also have a domain of all real numbers. Does this mean that h of x has a domain of all real numbers? No, it actually does not. And if you take a moment to look at the resultant, it should become pretty obvious as to why the domain of h of x is not all real numbers. Okay. Let me highlight this for you. Okay. Since we have a division, we have to avoid certain numbers. Okay, and those numbers is basically anytime my denominator is equal to 0. So x minus 2 cannot equal to 0. So this is easy enough. So basically it just means x cannot equal to 2. So the domain for h of x is not all real numbers. The domain of h of x is all real numbers except for 2. So x cannot equal 2. If x is equal to 2, then you get a division by 0, which kind of breaks the function. Okay. There we go. So keep that in mind when dealing with quotients of functions. Just like other rational functions, you must take into account that the domain is going to be restricted in addition to whatever the denominator function, whatever the domain of the domain of the denominator function is. You have to take into account also wherever the denominator function is equal to 0 must also be a restriction. Okay. So keep that in mind when you are asked to find the domain. A range for this particular function, easiest to just look it up in or look it up, or graph it and look at the graph. But I can tell you right now that the range for this particular function, because it's a rational function, and the only restriction is x cannot equal 2, the domain will be all real numbers. Oh, except for it cannot equal, y cannot equal, I think, oh, well, let's just graph it. Thought I could do it easily without too much math, but I'll just graph it. Alright, so the function was x minus 3 divided by x minus 2. Oh, another bit, there we go. There. Then we have an asymptote and it looks like 1. There we go. So our domain, based on the graph, y cannot equal to 1. Okay. As an exercise, you can determine it algebraically, because remember from our rational function chapter, you can change this to be of the form, not mistaken, some number over x minus 2 plus some other number called b, like that. So if you're asked to find the range, you can always do this calculation to help you figure it out. Or just graph it. Graphing it works. Okay. Alright. With that, here is your assignment for the day. Okay. Keep in mind for question C3, I asked a very similar question on a previous test back when we were talking, I think it was in the polynomial function chapter. Okay. But you guys should be able to do it regardless. Whether you remember that chapter or not, what we talked about in this chapter, you guys should be able to do it. It requires you to maybe go backwards a little bit. Alright, good luck. And if you guys have any questions, you know how to contact me.